Hi, welcome to Math 325, Linear Regression 1. In this particular lesson, I want to discuss some of the basics of matrix operations as they apply to our linear regression model. Many of you will have seen these operations in your linear algebra course or a linear algebra course you may have taken elsewhere. So fundamentally, I just want to go over some of the basics of matrix algebra. The most important takeaway for today is I want to show you how to use Excel to perform some of the matrix operations that are going to be useful for us as we use matrices to help analyze our linear regression model. So a matrix, what's a matrix? A matrix, as you know, is a rectangular array. We talk about the size of a matrix being the number of rows by the number of columns. We say a matrix is square if its number of rows equals its number of columns. A matrix containing only one column we call a column vector. A matrix containing only one row we call a row vector. We talk about the transpose in a matrix. Essentially, that's an interchanging of the rows and the columns. Two matrices are equal only if they are equal element by element. Therefore, they have to be the same size. So every element in a matrix has to be equal to every element in the other matrix for them to be equal. A scalar, it's an ordinary number or symbol representing a number. In multiplication of a matrix by a scalar, every element in the matrix gets multiplied by that scalar or number. If every element has a common factor, that scalar, can be factored out. We talk about matrix multiplication. Now this is extraordinarily important. We're going to do a lot of matrix multiplication in analyzing our linear regression model. And we have to understand that the matrix A times the matrix B is not necessarily equal to the matrix B times the matrix A. They have to be conformable. That is, the size has to be right. The number of columns in the pre-multiplying matrix has to equal the number of rows in the post-multiplying matrix. And there's a great discussion of this on page 183 of our textbook, so I urge you to take a look at that. The resulting dimension, that is the product matrix, has the number of rows associated with matrix A, the pre-multiplier, and the number of columns associated with B, the post-multiplying matrix. We talk about a symmetric matrix. Now again, this is going to be very important to us in multivariate statistical analyses. We're going to look at a lot of matrices when you get to that particular course. But for us, we're going to see that our variance-covariance matrix is also symmetric. And what does that mean? It means that if a matrix is equal to its transpose, then we have symmetry. A diagonal matrix, it's a square matrix whose off-diagonal elements are all zeros. So we have this diagonal that has some values on it, and everywhere else we have zeros. We call that a diagonal matrix. A particular diagonal matrix of great interest is the identity matrix, and that's the diagonal matrix which has ones on the main diagonal. And in general, if we take a matrix A and multiply it by the identity matrix, then the result is A, and it doesn't matter whether we pre or post multiply that matrix by the identity I. A scalar matrix, on the other hand, is a diagonal matrix that has a scalar value, a number, a symbol, on the main diagonal. We talk about vectors being linearly dependent or linearly independent. And it's going to be very important for us to be able to ascertain whether or not a data matrix that we have, for example, when we deal with multiple linear regression models, consists of independent column and row vectors. We say that a set of vectors in a matrix is linearly dependent if one of the vectors, that is, if one of the columns, can be expressed as a linear combination of the others. Now notice in the particular example that you see here, column vector 5, 10, 15, that's column 3, is 5 times column vector 1, which is the 1, 2, 3. And so we have linear dependence in this particular matrix A on this particular slide. If no vector in the set can be so expressed, that is, if no vector can be written as a linear combination of the other column vectors, then we say we have a set of linearly independent column vectors. The rank of a matrix is defined to be the number of linearly independent columns in the matrix. And again, this is going to be very important to us when we start finding the inverse of matrices. The rank of a matrix is unique. It can be defined as the maximum number of linearly independent rows. So if it can be defined as the maximum number of independent rows and the maximum number of independent columns, then clearly the rank of a matrix cannot exceed the minimum of the number of rows or the number of columns. Just think about that for a few minutes. In matrix algebra, the inverse of a matrix is another matrix denoted by A inverse, A with a -1 superscript, such that the inverse of the matrix times itself returns the identity matrix. An inverse of a matrix is only defined for square matrices. However, just because you happen to have a square matrix doesn't mean that it has an inverse. And that goes back to this notion of linear independence. If you have a square matrix and the column vectors or row vectors are not linearly independent, then you don't have rank which is sufficient to guarantee an inverse. And again, this is going to be very important to us later. I'll have more to say about it when we get to Chapter 6, Multiple Linear Regression Models. If a square matrix does have an inverse, the inverse is unique. An inverse of an R by R matrix exists if the rank of the matrix is R. So we have this square matrix. It has R rows and R columns. And if the rank of that matrix, which is the number of linearly independent rows or columns, equals R, then we know we have an inverse. Now, to find an inverse of a matrix, well, there's lots of ways to do that. All of them involve a lot of arithmetic, and so we're going to be happy letting the computer do that for us. Now, here's some basic theorems for matrices. These can be found in any elementary linear algebra textbook. I would ask you to read them over, convince yourself that you understand the nature of these theorems and why, in fact, they are true. In fact, some of you could prove these, and maybe you did when you took a linear algebra course. Now notice, down towards the bottom, next to the last bullet, the transpose of the transpose returns the original matrix. That should make sense. The transpose of a sum is the sum of the transposes. The transpose of a product, now notice what happens here, is the product of the transposes, reverse order. AB transpose is B transpose times A transpose. And likewise for A times B times C transpose. Now talk about the inverse of a product of two matrices. The inverse of A times B, again, is the product of B inverse times A inverse. Notice the switch, the reversal of the order. A inverse inverse returns A. A transpose inverse is A inverse transpose. We talk about systems of equations, which is what A times Y equals C could be used to represent. And those of you who have had linear algebra, all of you, I'm sure, recall then how to find this vector of unknowns y. We multiply both sides of that expression A times Y equals C by the inverse of A. And we know the A inverse times A on the left-hand side produces the identity matrix. And so we're left with Y equals A inverse times C. So if we can find the inverse of this matrix of coefficients in that last bullet, then we're off to the races. But we have to remember every square matrix does not have an inverse. This notion of rank, this notion of linearly independent rows or columns is important. Random vectors. Now we're getting into statistical analysis and the idea of random variables. A random vector or random matrix is a matrix or vector that contains random variables. So we talk about our linear regression model, and we know that the observations are random variables, so we can talk about then the observations vector, y, will denote it as being a random vector. So for example, suppose we have 3 observations from a linear regression analysis that we're engaged in. We call those observations y1, y2, and y3. And of course, those are random variables. Though values of those are dependent upon the particular model that we're investigating. The expected value of that random column vector then is nothing more than the expectation of the individual elements in the vector. The variance-covariance matrix of y. We talk about these 3 observations, y1, y2, and y3. We can talk about the variance of y1 and the covariance of y1 with y2, which is exactly the same thing as the covariance of y2 with y1. So we see that these off-diagonal elements are certainly equal. The covariance of y1 with y2 is the same as the covariance of y2 with y1. The covariance of y1 with itself is the definition of the variance of y1. And so a variance-covariance matrix is such that the variance of the random variables is on the diagonal, the covariances are on the off-diagonal, and clearly this is a symmetric matrix because of the nature of the covariance computation, which you all saw, I'm sure, in an elementary statistics course. Matrix operations using Excel. Now, this is, the meat and potatoes of today's presentation. I want to show you how to perform matrix operations using Excel. It's pretty simple, but you have to keep a few things in mind, and that is the nature of how you multiply matrices, the nature of how you find the transpose, etc. So I want to go over some of this with you. Now, we're going to use this data in the GPA data.xlsx file, which we've already worked with previously. And we actually did a linear regression of GPAs on the exam scores, if you'll recall. And so you've seen this regression done, and you know the results, and so you can compare the results that we get using matrix algebra with the results that we got using the algebraic formulas or Excel data analysis toolpack to do the regression. And I'll remind you of what those results were. So here's what we want to do. We want to find y transpose times y. I'll show you how to do that lickety-split. You'll notice that that matrix multiplication produces the sum of the y sub I squared. We're going to want to compute x transpose times x, where x is going to be this matrix that has its first column being 1s, and I'll talk a little bit about why that's going to be important to us in the next presentation when we actually discuss the notion of using matrices to construct our simple linear regression model. And you'll notice when we do this arithmetic of x transpose times x, that it's a symmetric matrix. Then we're going to find its inverse. Then we're going to take x transpose x inverse, and we're going to multiply it by x transpose y. And what you're going to notice there, gang, is that that computation produces the estimated regression coefficients b0 and b1. So if we have the estimated regression coefficients b0 and b1, and we hit the matrix x by them, that is x times b, where b is the column vector of estimated regression coefficients, then we're going to get our fitted values, y hat. And if we take y minus y hat, we're going to get our residual values. And if we take our residuals and square them and add them up, which we can do by taking the transpose of this vector E multiplied by the vector E, we'll get sum of squares there. All this will make sense, I hope, as you take your time and wade through the arithmetic associated with this. So here's what I've got, and you can see it as well as I. We've got our exam scores, and we've got our GPAs. Exam scores are X, GPAs are Y. So over here, I've taken and written the y column vector. It's a 20 by 1. Now remember, matrices are defined by rows by columns. So I got a 20 by 1 column vector, or 20 by 1 matrix called y. And the first thing I wanted to do was find y transpose. Now, it's important for you to know what the size of Y transpose is going to be before you can actually find it. So we know that Y is a 20 by 1, so we take the transpose of it, we're going to get a 1 by 20. Now what you need to do then is you need to carve out a spot on your spreadsheet which is 1 by 20. Now watch the toolbar, and in this case I have to enter the formula equals, sorry, I hit the shift key inadvertently, equals, now transpose is the function, and what do I want to take the transpose of? I want to take the transpose of this matrix Y, which is over here in column G, and so I just scroll over top of it, then I close the parenthesis. Now this is the most important part of using Excel. Don't simply hit enter, but hit Control Shift Enter, and when you do, voila, Y transpose is created. Now this thing called transpose is what we call a matrix operation and an array function, and so you'll notice now that once I've entered it, that array function up here in the toolbar is enclosed in brackets. That happened as a consequence of using Control Shift Enter. Now what's the next thing I want to do? I want to define Y transpose times Y. Now again, it's important for you to know the size of Y transpose times Y. Well, Y transpose is a 1 by 20, and Y is a 20 by 1. So if you take a 1 by 20 times a 20 by 1, you get a 1 by 1. So in this particular cell, N7, I'm going to enter the formula equals MMULT. That's matrix multiplication. Now order is important. So I want to grab this 1 by 20, which represents the vector Y transpose, comma, pay attention to the toolbar, comma, and now I want to go back and get Y, which is this 20 by 1. Now again, I'm going to close that parenthesis, and I'm going to use Control Shift Enter, and when I do, I get 134.84. Convince yourself that if you took the Y's, squared them, and added them up, you would get 134.84. Now here's the matrix X as I've defined it. Here are the exam scores. I've included this constant 1 column, and you'll see why when we discuss our simple linear regression model using matrices in our next presentation. But again, to find X transpose, notice I just used the transpose function. I've already done it, so I'm not going to do it again. To multiply X transpose times X, it's the same deal. Now notice in this case, X transpose is a 2 by 20. So we got a 2 by 20 X transpose times a 20 by 2 X, so that gives us 2 by 2. Notice the symmetry. We got 100 on the off diagonal. Now to find the inverse, let me just do it over here. We've got X transpose X, it's a 2 by 2, so the inverse of X transpose X is a 2 by 2. So the first thing I have to do is carve out a 2 by 2 region equal M inverse. Now you can look all these formulas up if you need to, but M inverse, matrix inverse, is the formula that one uses to find the matrix, or find the inverse rather, of a matrix. Now we want the inverse of X transpose X, which is up in this area here, N15 through 06. Close the parenthesis, Control Shift Enter, and again, I've already done it. Thankfully, it's the same. Now we take X transpose times Y. Now X transpose was a 2 by 20. Y was a 20 by 1. So if you take a 2 by 20 times a 20 by 1, you get a 2 by 1. Lo and behold, there's X transpose times Y. Now I want you to go through this. This is just another matrix multiplication situation, which I've already done. Now if I take X transpose times X, which is up here, this 2 by 2, inverse rather, here, this 2 by 2. X transpose X. I couldn't figure out how to make the 1, the minus 1 sign, so I just have a minus sign. I hope you understand that. So we're going to take X transpose X inverse times X transpose Y. Here's X transpose Y. Here's X transpose X inverse. 2 by 2 times a 2 by 1 results in a 2 by 1. Notice, pay attention, the minus 1.699, that's B0. The 0.8399, that's B1. Those are indeed the estimated regression coefficients. And if you want to demonstrate, the veracity of that, just go back to the lesson where we actually built the regression model, and you notice that those coefficients, I used the data analysis toolpack in Excel. There they are. They're the estimated regression coefficients using the regression procedure from Excel. Or if you wanted to use the formulas, the algebraic formulas, you can do that too. The bottom line is X transpose X inverse times X transpose Y yields B. So now I say, well, let's compute Y hat. Well, how do we find Y hat? Well, we take our X observations, multiply them by B0 and B1. Now I hope you have an idea why we needed that 1 in the X matrix, because that's our intercept term. So we're going to take 1 times B0 plus B1 times the X value. Well, that's nothing more than X times B. So again, X is my 20 by 2 up here. Here's my matrix X. It's 20 by 2. And I'm going to multiply it by this 2 by 1 here, this matrix, this column vector B. And so I'm taking a 20 by 2, multiplying it at 2 by 1, so I get a 20 by 1, and lo and behold, these are the fitted regression values. These are my Y hats. Again, if you don't believe it, go back and take a look at them. There they are, 2.91, 2.33, same thing here, 2.91, 2.33. Now if we subtract Y hat from Y, we get our residuals. So here's our residuals for our 20 observations. If we take the residuals squared and add them together, we get the sum of squared error. Again, we can do that using matrix multiplication. So what I've done here is I've taken this matrix, transposed it. See it? I've transposed that matrix of residuals, and then I've multiplied it by itself, this vector, to get the sum of squares there. Again, 3.406. If you need confirmation, go back, take a peek at the regression output, 3.406. So the bottom line is we can use matrix arithmetic to derive all of the results that we derived or computed when we were doing our simple linear regression model, regressing our grade point averages on these entrance exam scores that we looked at before. The important takeaway is the Control-Shift-Enter. It's hard as heck to find that in the Excel help manual if you forget it, so I've typed it out here again for you. Okay, well that's part 1 of chapter 5. I just wanted to give you a little overview of how to make the connection between linear algebra and some of the stuff that we're going to be doing in our linear regression models. Not so important for the simple linear regression model, but terribly important for the multiple linear regression model. Okay, take a look at chapter 5 in our textbook, and of course, do the suggested homework problems. I have a second part for chapter 5 that I'm going to create a presentation for, and that'll be available within the lesson too. So more to come.